Good morning, everybody. So, to refresh your memory real quick, on Thursday last week, we actually started an Atwood's machine problem. Fancy name for really just two masses connected by a string over a pulley. And we got about halfway through solving the question, which is the work shown. And I wanted to finish this off for you guys so you could try number 10 on WebAssign. And then also, slightly different, but number 11, which is a modification of Atwood's machine. Same rules apply though. And if you can get those, you'll be ready to go for the lab tomorrow, which is both this straightforward one and then the modified one like question 11 on WebAssign. So anyway, to kind of jump right back into it, mass 1 on the left is the smaller of the two masses, so it loses the tug of war, if you want to think of it like that. And it's going to accelerate upwards. So beneath it, you can see we have Newton's first law set up. Same idea for mass 2. It's the larger of the two masses, so it's going to win the tug of war and accelerate down. And I've got that Newton's second law set up. So that's where we got. And the biggest thing I want to remind you guys is when we do this, the direction of the acceleration is what we're going to call the positive direction. So this is the little tip I'm going to tell you guys, and it is the most effective way that I've taught this in the past to make it clear for you guys. So that being said, if I look at mass 1, since it's accelerating up, that direction is going to be the positive direction. So if you look at its FBD, tension is positive, but the weight of it is in the opposite direction, so that is negative. So in my Newton's second law down here, I'm actually going to just absolute value the weight, because sometimes when you use negative 9.8 it would be negative. I'm going to absolute value it though to make it a positive, and then recognize right in front this has to be in the negative direction. All right. For mass 1, you're probably like, that's what it always is. Up is positive, down is negative. So I agree. Why are we doing this? Mainly for mass 2. So when you look at mass 2, it's accelerating down. So for mass 2, when we get over here to the FBD, the downward direction is actually going to be positive. All right, so what that means is FG2 is going to be positive. So again, if you accidentally solve, or not accidentally, if you solve it the correct way, mass times negative 9.8, absolute value that to make it the positive direction, because it's going in the same direction as that mass accelerates, which is down. The force that's up then, tension, is actually opposite the direction, so tension actually needs to be negative. So this is the trickiest part with the problem. The way we solve it, all the problems, is you have to just stop and think which way is it going to accelerate, and then you have to recognize the positive and negative based on the directions. Okay? Once we get to this, so let me get rid of the FBD and just kind of zoom in here. All right, there's two nice things. Well, there's only one string, so tension in the rope is going to be the same. All right, just pulling in opposite directions, which we've clearly now shown with that little acceleration rule. The other variable that is actually the exact same is the acceleration, because they're connected by a string, so they have to change their motion the exact same way. The other thing too that's nice with it, if we choose the direction that they accelerate to be positive, these should both be positive, which is an easier way, I think, than trying to recognize one acceleration as negative, which is a different way to do it. All right, so I'm trying to avoid that confusion. So we've kind of done this before in the past, where if we have two equations that have two of the same unknowns, we can create a system of equation. All right. I'm not going to give you guys numbers for this. All I'm going to do is actually solve these equations for the force of tension. And I can do this with the mass 1 equation by just using moving the weight to the other side. Keep writing the subscript 1 so you don't confuse it with the weight of mass 2, or even right here, mass 2. Try to show that detail. So now I have an equation for the force of tension, and then over here I'm going to move force of tension actually to the right side. All right, so then it'll be the weight of mass 2 And if I want tension by itself, if I'm moving it to the right, I'm going to have to move the M2 times A to the left, so I'm just kind of trading places. Moving the M2 times A to the left is subtraction, though, because I would have added FT to the other side. And now I clearly have two expressions that are both equal to the tension. And again, as long as it's one rope, it's the same tension, so I can just set them equal. Substitution, whatever you want to call it. So then, if I do that, I've got the weight of mass 1 plus mass 1 times the acceleration equals the weight of mass 2 minus mass 2 times the acceleration. All right. From here, what I would ask you to solve for, of course, would depend upon numbers, but let's just say we want to know the acceleration of the system. We knew in our FBD, since the masses were different, it would be unbalanced and that it would accelerate. So let's just act like it's going to be a straightforward, what's the acceleration? Well, again, these accelerations are the same, all right? So let's try to get those expressions to the same side. So I'm actually going to move this back to the left by adding. All right, and I'm going to move this to the right by subtracting. So I'm going to have mass 1 times the acceleration plus this being brought over to the left side, mass 2 times the acceleration equals weight of mass 2 was already over here, and then like I said, I'm going to move the weight of mass 1 to that side. So that would actually be then subtraction. I'm going to talk about that in a second because that should actually make sense. All right, last thing then, or two things. Since the acceleration actually is the same because the masses are connected by a string which forces them to change their motion the same way, I can actually factor that out. So I'm going to have mass 1 plus mass 2 times the acceleration of the entire system. All right, nothing happened on the right side. And then, to finish it, I can take the system's mass, so the entire system's mass, M1 and M2 added up, since it's being multiplied by the acceleration, I can divide it to the other side. So my final equation, let's jump down here, it's basically going to be the sum of the forces that are playing tug of war, which, as I was kind of about to say earlier, it's interesting to think about. F2 is the larger, so mass 2 is the larger of the two forces. So it makes sense that it should win the tug of war, so that is then why F1 is being subtracted. Because they are opposing one another, and F2 is the larger, which we decide to call that direction that accelerates a positive. Then the other thing is, they're not just actually playing tug of war over one mass, they're playing tug of war over the whole system, so it should be divided by the system's entire mass. All right. So the math is a bit detailed because we had to do substitution of two equations. We have done that before though. The trickiest thing though, where issues usually occur, is knowing the direction of positive and negative. So one more time, the direction that the mass accelerates. So this one up, this one down, we call that positive when you then apply Newton's second law. So take your time with that because that is usually where details are missed and we get a little confused, okay? All right, guys, go ahead and try number 10. You should be able to easily do that. It's very similar to this one. And then I would also try number 11, just so you have an idea. Even if you do get stuck, you have an idea if I give you some guidance tomorrow, okay? All right, good luck, guys. Have a great day today.